So the purpose of this video is to explain the very important concept of conjugate pairs. And we're going to use an example where we've got a binary dependent variable. And it's going to be based on coin flips. And we're going to take the example from Krushki, where we've got a coin that's made by Acme coin manufacturers, and we don't know in advance that the probability of it turning up heads is going to be 0.5. So these are novelty coins and might not necessarily have a probability of 0.5 of turning up heads. So what we're going to have, because it's a binary dependent variable, we're going to have heads. We're going to view those as successes, and we're going to say that means that y is equal to 1, and alternatively, a tail is a failure, means y is equal to 0. So we're going to do an experiment. And we're going to do an experiment, and we're going to get 3 heads in 7 trials. And we're going to represent this as z is equal to 3 and n is equal to 7. And our goal is to come up with a posterior distribution of the parameter theta, where theta, when we got a binary dependent variable, is associated with a likelihood function that's going to be Bernoulli / binomial. So that's what theta is, and we can think of theta as being the expected value of the random variable capital Y, where this random variable can only have these 2 possible outcomes. So if we think about Bayes' theorem, the posterior distribution of theta given data is equal to the likelihood function, the probability of data given theta, multiplied by the prior, divided by the marginal distribution of the data. And here is where the magic comes in. If we've got a binary dependent variable, then our likelihood function is going to be a Bernoulli binomial. And the magic consists in the fact that if we can specify our prior as a beta distribution, then we're going to very easily be able to obtain a posterior, which is also going to be a beta distribution. In fact, what we're going to see is that if our prior is a beta with parameters a and b, then the posterior is also going to be a beta, but it's going to have parameters a star and b star, where a star is equal to a plus z. So we've got our a here and our z here, and b star is going to be equal to n minus z plus b. So there's our n, and there's our z, and there's our b. So let's do a worked example. And I should note that although I referred to this as magic, the proof is shown in section 4 of this week's notes. But anyways, we want to do a nice concrete example. So we just clean this up a bit for a moment. And so what we're going to do is we're going to assume that we got Z is equal to 3 and N is equal to 7. And so we need to specify our prior. So we're not exactly going to specify it as a beta AB. Rather, what we're going to do is we're going to use Krushke's approach of specifying it in terms of omega and kappa, and then we're going to convert to A and B. So I'm going to say that omega is equal to 0.2, that kappa is equal to 20. So this means my best guess of the mode for the distribution of theta is 0.2, and the concentration is 20, which means not in any exact sense, but approximately. How much confidence do I have that the mode is equal to 0.2? About as much confidence as I would have had I tossed the coin 20 times and used those data to arrive at a value of 0.2. So even though in my mind I'm going to parameterize according to omega and kappa, to get this process to work, we're going to have to convert from omega to kappa to A and B. And as we saw in the previous video, that's not tough to do, because if we've got omega and kappa, then beta AB can be expressed as beta omega times kappa minus 2 plus 1. That's going to be our A. And our B is going to be 1 minus omega times kappa minus 2 plus 1. So if we know that omega is equal to 0.2 and kappa is equal to 20, then what we've got is a beta distribution of 4.6, 15.4, and then we apply our magic. And our magic says that if this is our prior, then our posterior is going to be beta A star B star, where A star is equal to A plus Z, and B star is equal to N minus Z plus B. And we know what A and B are. And we also know that Z was equal to 3 in N equals 7 trials. So we can just put all that in. And what we can say is that our beta, A star, B star, is equal to beta A plus Z, N minus Z plus B. And with all that information, we know that we've got a beta 7.6, 19.4. And then if we want to, what we can do is go to E-class, where we've got this program beta prior generator, and it's an R program. So we can start off with our prior, and we can visualize that and say, okay, yep, that's a good prior. That captures my thinking. That captures my thinking about what my prior beliefs are about theta. We know Z equals 3, N equals 7. We do the algebra and say that according to the magic, our posterior should be a beta 7.6, 19.4. We put that into beta prior generator, and what we get is a posterior distribution. So the whole idea about conjugate priors, conjugate pairs, is it provides us a very simple way if we specify our prior as a beta distribution, if we collect our data like that, then it's very easy to calculate the posterior distribution.